Alright, so new section with a lot of old vocab coming back at you. The intention is to prep you guys for calculus. The point of calculus in this part of the calculus section of their course is that you should be able to analyze graphs without the use of a graphing calculator. So you are going to be the graphing calculator when you get to calculus. That is not true yet for pre-calculus, however. So I'm going to give you the rundown of essentially what's the fundamental theorem of algebra that leads into the fundamental theorem of calculus. That sounds like a big deal, doesn't it? It's a big deal, which means you should be able to tell me all about different polynomials without doing any graphing calculator work. So before we get to the lesson today, a little quick rehash on how we factor some fancier polynomials. So these are not from that worksheet that you picked up for homework. Those are just for you to explore on your own. But when I look at these examples, I notice that these are polynomials that are set equal to 0. So not only do we have to factor them, they would want me to take it further and actually solve the factors. So I look for common factors first. There are no common factors in this trinomial. So then we look at this as like a reverse foiling question. So I look through the terms and I think, okay, my lead terms have to multiply to give me x to the 4th this time. So we do have higher degree than normal, but it doesn't change the factoring process. So you could use x to the 3rd, x to the 1st. You could use x squared and x squared. You have to look further into the question to notice which one you want to use. And since I want my arches to add up to negative 4x squared, that means we have to use x squared. And then at the end of your factoring question, I want them to multiply to 3. 3 is prime, so it's got to be 3 and 1. And then Daniel's telling me, why don't you use negatives? Why do we have to use negatives, Daniel? Whoops. Yeah, we need the arches to add up to negative 4. Very good. Now your Algebra 2 teacher would argue this is not fully factored. Which factor can easily factor more? This one right here can factor more, right? But if the nature of your question says to just solve it, it doesn't have any extra instructions on it, technically you could stop your factoring process here and go ahead and solve it. If you set this equal to 0, and then you set this factor equal to 0, you're going to get 2 solutions here and 2 solutions here. Tell me why. What happens right here? You're going to add the 3 and then you're going to square root. So you get both positive and negative square root of 3. And then over here, you'd add the 1 over, and then you square root both sides. So again, you get positive and negative 1, because square root of 1 is 1. Okay. Now, that we could kind of take the liberty of that shortcut because of the nature of the question. We're going to have to get really good in PreCalc about reading the directions on the questions. Because sometimes I will say, it'll be like a 4-part question, and it'll say, completely factor the polynomial in terms of its linear factors. These are not linear factors, so we'd have to take this further. I'll show you today in the lesson what it looks like to take them all the way down to the linear factors. Okay, that's enough warm-up for today. Let's talk about stuff. You actually kind of know all this. You just don't think about it very often, I think. Your polynomials, which we had been working in monomials for a while, back on 2.1. Now we're going to see some larger scale polynomials that has more than one term. You should be able to first identify for me what is called the leading term. What does it mean to you in a polynomial when you have the leading term? Who are you looking for? Well, most kids say the first term. Is that always true? No. Because what if they get sneaky, and I think they do in a moment on your notes. What if they have 3x squared minus 5x to the 3rd plus 2x? Who's your leading term? Yeah, your leading term is actually this guy. Someone is trying to be sneaky and put it out of order. So they have to go in descending exponential order. That's the term order for polynomials. So then when I say, who is your degree? What is, by definition, your definition, the degree of a function? Of a polynomial, excuse me. It's the highest exponent. So in this case, that signifies you have a degree 3 polynomial, which today we're going to talk about it being an odd degree. And then the lead coefficient. Who is the coefficient in front of that leading term? Yes, his coefficient is a negative 5. So think about this, guys. Without touching a calculator, you should have it's not going to be a good one, but a basic picture of what this polynomial looks like, at least on the ends. If you have a cubic, an odd degree polynomial with a negative 5 in front of it. Now cubics normally look like this, right? I don't care about the middle, but the ends normally look like that. Is this cubic going to look like that? No. Because it's got a negative lead term. So what happens? It's going to be like this. Okay. So all those end behavior questions that we ask you guys, you should be able to come up with polynomial end behavior without touching a graphing calculator. Okay. I'm still going to draw like little ends, and sometimes you guys will just point your fingers up and down, and I'll know what you mean by that. But then we got to transfer it back to end behavior. All right. So some vocab, who's the degree, who's your lead term, who's your lead coefficient. You should be able to tell me all that. I'm going to skip over this stuff. This is on your notes now. This is a visual example of what a polynomial is. So this right here, this is a visual example of a polynomial. His domain has to be negative infinity to infinity, so it has to stretch forever left and right in some way. There can be a bunch of wiggles and curves and stuff in the middle. There could just be one. But a polynomial function is a smooth, continuous function. No sharp edges, no jumps, no oscillations, no breaks. These two examples are visual examples of not polynomials. Right here. This is called a break or a jump. This is not a polynomial function because of that reason right there. And then this one bothers kids because they don't feel like this is not smooth, but because of the definition in math for polynomials can't have sharp corners, this is considered a sharp corner. This is an absolute value function, right? If you think about absolute value functions, they're like have the absolute value bars on them. That is not what an algebraic polynomial looks like. So if you want to break it down to what the algebra looks like, no, it's not polynomial. The graph, because of the sharp corner, is why it's not a polynomial. All right. This is blabbing about monomials. Should make y'all do the graph dance. I'm not gonna though. All right. Skip the transformations part of this notes. We'll talk more about that later. Okay, here we go. End behavior. You should be able to give it to me without touching your calculator. You're going to perform what's called the lead term test. Once you identify who your lead term is, you're going to look at his degree and his signage, and you're going to be able to just sketch the ends. I don't care about the middle. Give zero hoots about the middle. And then you can fill in your end behavior template. So this is our interpretation of the graphs. If you have an odd degree, so like x to the third power, x to the fifth power, and so x to the first power, and you have a positive lead coefficient, you should know that the ends go down on the left and up on the right. I do not care what happens in the middle for end behavior, just the ends. But if you still have an odd power, odd degree I should say, but now you have a negative lead term, you guys told me that reflects. So the left side goes up and the right side goes down. Again, I do not care what happens in the middle. I'm just looking at end behavior. This is actually how they used to do end behavior back when you guys, like about 12 years ago, we didn't have you guys write the end behavior template when you were in like little kid math. They just had them draw the ends. It's pretty lame actually. All right, so now if you have an even degree with a positive lead term, that means you're a cousin of a quadratic, right? So your ends go up, up if you have a positive lead coefficient. But if you have an even degree with a negative lead term, your ends would go down, down. And you guys already knew that. So let's fill out this chart. Write an example of a function that has even degree with a positive lead coefficient. Okay. How about 3x to the fourth plus 2x? Does that work? Okay. I do not care what the middle looks like. All I want from you is what the ends look like. So, even degree. So they both go either up, up, or down, down. Which one is this? So all I want you to do is draw your ends up, up. Don't care about the middle. But if you change this polynomial to have a negative lead coefficient, how will that change your end behavior? They'll go down, down. Now, when you compare that to an odd degree, so like an example of an odd degree polynomial, I don't know, I'm just making stuff up here. 4x to the fifth plus 1. Don't care what happens in the middle, what happens on the side, on the ends. The left side will move down, and the right side will move up. But if you take that polynomial and you give me a negative coefficient instead for the lead term, the left side starts up, and the right side is the one that goes down. So that's the first thing I do when I have to sketch or when I have to come up with end behavior and I'm not supposed to use a calculator, is I do the lead term test in my head and I just sketch the ends. I don't care about the middle at all. Okay, and I'm really bad about this little notice here, so correct me when I make a mistake during the video here. Sometimes I say things like, is it even or odd? And I really should be more specific because we just had a whole chapter where we talked about even and odd functions, which was referring to symmetry of your functions. What I need to be saying today is we have a polynomial of even degree, or we have a polynomial of odd degree. So if I try to shorthand it and say like, is it even or odd? Like I got to get more specific. So I'm trying. All right, so here they have end behavior, but they're writing as limits. Remember, guys, we don't do limits for end behavior. You guys do this. And this question is very thoroughly done, and there's nothing wrong with what they did. They went to the graphing calculator, and they literally graphed it on the graphing calculator, because I don't think we had to go that far. There's going to be a lot of questions on your homework where you're going to waste a lot of time graphing on the calculator. Look at your function. Your lead term is 2x to the fourth, so that is an even degree with a positive lead coefficient. So doesn't that mean the ends go up, up? Because cousin of a quadratic with positive lead term would go up, up. So I don't think we need to grab the graphing calculator for this question. I think you guys could have told me it goes up on the left and up on the right. Whoops. Just as easily as you could have graphing it. So that's my challenge to you guys. Try not to use the calculator today when you don't have to. That's boring. It's the same thing. Uh-oh, Hofbauer wrote careful on this one. So be careful. It's not in your notes. Just look at the board. Why do you have to be careful on this one? Yeah. This is not in standard form. So your lead term is actually this. So you have an odd degree polynomial function. You have a negative lead coefficient. So normally odd degrees go down and up like this, but is this one going to do that? No, this one's going to go up on the left and down on the right. So just be careful. Sometimes they're like out to get you and they put a polynomial. You know who does this a lot? And it's not me. And it's not Hofbauer. It's the SAT test. Yes. I feel like 3/4 of that test is just seeing if you can read. Turns out the answer is no for some of us. Okay. So here's some vocab coming back again. I talk about maxes and mins being called extrema. We kind of already talked about that in a previous lesson. We know they're called turning points. Anytime your function changes from increasing to decreasing, you have a turning point. In calculus, they're called some other things as well. They refer to them as turning points in particular. But we should be able to interpret how many turning points our function has based on the degree of the function. So somewhere in your notes, and it should probably be on the front of your notes somewhere because there's not a real great spot here. I need you to write this down. Okay, whatever the degree is, that is equivalent to the maximum number of possible zeros. So another word for zeros, by the way, is solutions. Some people will say x-intercepts is the same thing as a zero. I kind of argue that because we talked before about how sometimes x-intercepts, zeros aren't always synonymous. It's one of those every x-intercept is a zero, but not every zero is an x-intercept thing. Don't get hung up on that today. Okay, and then here's the other thing I want you to write down. Whatever the degree is, if you take one away from that, so they call it n-1, that is the maximum number of possible turning points. So today in PreCalc, we're going to investigate polynomials without a calculator at first. And I'm going to say, tell me how many possible zeros you could find, and you're going to give me that answer real quick. And then I'm going to ask you, how many possible turning points could you find? And you're going to give me that answer real quick. I'm not going to make you find the turning points without a calculator, but I am totally going to make you find the x-intercepts and the zeros without a calculator. Okay? We got this. You know, how dare I? Because you can factor. Yes, you can. Now, on the back of your notes, if you guys could flip quickly to 3B, we're going to come back to 3A in a minute. They kind of go through the differences between x-intercepts, zeros, solutions, factors, and how they're all kind of related to each other. An x-intercept for us is technically when it crosses through the x-axis, but your book also claims anytime it touches the x-axis is an x-intercept. So if you have an x-intercept at a value of like x equals c, your book also calls that a zero of the function. You guys know that as a solution to the function. So solutions mean if you set your function equal to 0 and you solve it, that's how you find solutions. Now you're going to see today, for us, that means a lot of factoring in your future. Speaking of factors, if you know you have a solution at a certain value, you could write it as a factor. So if you know you have a solution at x equals 2, that means you could go backwards one step and write the factor as x minus 2. We'll come back to that big time over the next few days. All right, we got a lot of quadratics coming up. Flip back to 3a. This one's already done for you. So what we would have you do on your homework and also on your tests, we would have you start looking at the polynomial function, which is up here, and you investigate and perform what's called the lead term test. So the lead term test, there's your lead term. It's a cubic, so an odd degree polynomial with a positive coefficient. If they asked you about end behavior, we could easily come up with it. But today, all they wanted from this question was state the number of possible real zeros and turning points. So the possible number of real zeros, this is just the degree. So what degree was it? 3. Good. So it has at most 3 distinct real zeros. And then the number of turning points is whatever the degree is, but 1 less than that. So that's why it says it has at most 2 turning points. So there's going to be a question on your test where that's all you got to do. How many possible zeros and how many possible turning points? And then you're like, whoo! And then I don't want you to find the turning points, but what I do want you to do is find the zeros. So what they do is they take the polynomial, they set it equal to 0, and they solve it. So recognize that this polynomial is a 4-term factoring question. Do you remember the method for how we solve factor 4-term problems? Grouping. So they take the first group, and they look at the last group, and they factor out what's in common. So in this first group, they factored out an x squared, and they're left with x plus 2. And then in the second group, they factored out a -1, and they're also left with an x plus 2. Do you remember grouping was the one where you needed the parentheses to match? Once the parentheses matched, they left the x plus 2. Technically, they factored it out of the problem. But they were still left with an x squared and a -1. That's where this factor comes from. Now, your Algebra 2 teacher would argue to the moon and back that this was not fully factored. And they would expect you to continue on and factor x squared minus 1 into x plus 1 times x minus 1. But your PreCalc teacher would argue, if your only job is to find the solutions, you could have stopped right here. Because if you set this equal to 0, aren't you going to get positive and -1? And if you set this equal to 0, you're going to get x equals -2. How many solutions did they find? 1, 2, 3. And isn't that what they said they were supposed to find at most 3 solutions? So they did. We'll learn later when and why sometimes you don't find all 3 solutions. They don't disappear. They're there. All right, on the back, please. 4a. So do a little investigating without a graphing calculator. You should be able to tell me the maximum number of possible real zeros. Yes, it is whatever the degree is. So the answer to this one is 4 because of this guy right here. And then the possible number of turning points. Yep, it's whatever the degree is minus 1. So that would be a 3. And now they want you to actually take algebra and factor it. So we're going to take our polynomial, x to the 4th minus 9x squared plus 18. I want you to factor it and find your zeros. All right, y'all. You caught on to what we do when it's x to the 4th in the lead term? We use x squareds, right? And then at the end of your factors, you want your back numbers in your factors to multiply to 18. But I need my arches to add up to -9. So how about we do a -6 and a -3? Now for today, because all the instructions said was factor and find your solutions, you could stop right here. And you could set your factors equal to 0 and solve them. But I'm going to show you a little secret in a minute. right, solve this with me. Add the 6 over. And then when you square root, what answers do you get? Plus and minus the square root of 6. So you just got 2 solutions right there. And then same thing over here, right? You add the 3 over, square root both sides, and you get plus and minus square root of 3. So how many total solutions did we get? Yeah, which is kind of what we were promised. They said you can have up to 4 solutions, and we got them. All right, this is a little higher level thinking, so if you're like a little lost after this one, don't panic. We'll talk about more of this later. What if my directions said you need to write this in linear factors? Because what I have right here, these are not linear factors. These are quadratic factors still. Huh. Has anyone ever tried to factor x squared minus 6? Because you can. Like, why? Because of a moment coming up in PreCalc, right? If this said x squared minus 9, none of you would have batted an eyelash at me. How would you have factored x squared minus 9? X plus 3 and x minus 3. And you got that by performing the difference of 2 squares pattern. You took the square root of each of them and did 1 plus and 1 minus. So what stops you from doing that on any number? What if I just did x plus square root of 6 and x minus square root of 6? Isn't that the same thing? Yeah, because what's the square root of 6? The square root of 6. Boom. Just blew your mind with that, didn't I? So, being inspired by that, how could you technically factor x squared minus 3? Same thing. X plus square root of 3 and x minus square root of 3. So, if your teacher or your SAT test or your homework problem said you have to factor them all the way down to linear factors, these are your linear factors. Now, guys, look how beautiful this is. If you set each of these equal to 0, what answers do you get? The same answers, okay? So, you're like, well, why would I want to do that? I'm just trying to show you something a little sneaky about math. This does come up in a couple lessons from now where I will make you take them down to the linear factors. Okay. Not today, though. Today would just be for like bonus points in my heart, if you want any of those. Okay. Next one. Who's your lead term? You see him? Is it in the right order? Okay, cool. It's right here. So your degree is 5. So how many possible real zeros do we have? Real zeros is 5. How many possible turning points do we have? There we go. And now I want you to actually factor them. Okay, this is what I'm worried about. I kept warning you guys. I kept seeing people who weren't showing me work on this question. I'm a little concerned some of you don't know how to factor this. What's at the very top of your factoring flowchart as far as process? What are you supposed to look for at the very beginning of every factoring question? Common factors. Is there a common factor there? Yeah, who is it?
X.
So if you took an x out, then you're left with x times x to the 4th minus 6x squared minus 16. That's just the first step in your factoring. Now you got to keep going. Okay. So, yep, I'm hearing negative 8 and positive 2. So x squared and x squared. And then if you use a negative 8 and a positive 2. Now as far as like factoring, this is fine. You can stop here. But if you wanted to get fancy, can we all agree that this one can factor some more? If you want to get really fancy. Like, could you square root 8? It would be kind of icky, but we could. What about this one? Would you be able to factor this one more? No, because that pattern, well, okay. I'm going to say this with an asterisk next to it. I'm going to say no, because that pattern only uses the difference of 2 squares. You actually can factor that one, but you have to use an I. Let's look at why. All right, so real zeros. Guys, this is one of your factors. If you were to set this factor equal to 0, what y'all get? Yeah, x equals 0. If you were to set this guy equal to 0, you would add the 8 over. And then when you square root both sides, you get positive and negative. Square root of 8 breaks down into, so 2 squared to 2. What happens when you set this equal to 0? You subtract the 2 over. What happens when you try to square root the negative 2? You're going to get imaginary numbers. And it says right here, find the real zeros. So I don't have to worry about this one because it produces imaginary solutions. And you're like, what? Okay, so how many solutions did we find? We found 3 real solutions. These 2 are ugly, but they're still real. So how come, did you guys lie to me earlier when you said 5 zeros? Okay, so no, because first the rule says you can have at most 5 zeros, and a mathematician would argue you actually do have 5 zeros. There's 3 of them, where's the other 2? They're imaginary. They're there. We'll talk about what they look like when they're imaginary, just not today. They're there. They're just not real. We sound real crazy right now. Okay, I don't really think I need to graph this. Like, I surely would not grab my graphing calculator for this question if this was a homework question or a test question. I'm going to investigate the lead term. So, talk to me, guys. What kind of polynomial degree do you have here? Yes, it's 5, so it's odd degree with a negative lead coefficient. So dyslexic lady needs a little bit of a sketch, but not like a cool one. Just show me what the ends do. Odd degree, so instead of going down and up like this, because it has a negative coefficient, the end on the left will go up and the right end will go down. I do not give 2 hoots what happens in the middle. I'm just interested in end behavior. So I don't need my graphing calculator. I got this. Fill out your rubber stamp of end behavior template. I need to know what's going on the left side and on the right side. Okay. So on the left side, where's your end going? Up to infinity, and on the right side it's going down towards negative infinity. So investigating what's happening with your graph without a graphing calculator is kind of the prelude to calculus. Graph analysis with no technology necessary. Okay? Part of calculus, not the whole thing. Alrighty. It says skip for now, and I don't really know why. It's not really a hard question, but we'll skip it anyways for the sake of time. Alright, here's a possibly new topic for some of you. What does it mean when your zeros and factors are repeated? It means it has what's called multiplicity. So multiplicity means your factor shows up more than once. So we've seen things in factoring where like you had a quadratic, like x squared minus 6x plus 9. And if you guys went ahead and factored this, it'd be like x minus 3 times an x minus 3. Which you would often shorthand to x minus 3 quantity squared. Now, how many solutions does this quadratic give you if you set it equal to 0? Kind of 2, but it's the same solution, isn't it? Positive 3 just shows up twice. So then you're thinking, okay, like what does that mean for my graph today in pre-calculus? So this quadratic at x equals 3, you would see it do this. So back in like quadratic formula, we talked about like, oh, if the discriminant is 0, you just get the same solution twice. So we say we have one solution. What you actually have in this case is one solution with multiplicity of 2. So if you notice a solution or a factor showing up more than once, now you have to indicate the multiplicity. Before we get to what that looks like, I'm going to give you a little breakdown of multiplicity. If it shows up an odd number of times, so if it's like x minus 3 to the 3rd power, or x plus, I keep writing odd numbers, I don't know why. I don't need that to be odd. If it says x plus 4 to the 5th power, it's going to cross the x-axis. And the only reason I know it has multiplicity, well, 2 reasons. You're going to see it in the algebra, but the other thing you're going to see on the graph is instead of like just crossing through the x-axis, it's going to kind of hang out at the x-axis for a minute before it crosses. You guys will probably not recognize that on your graphing calculators. That comes with experience, okay? But you're going to see in the factor, it'll be like x plus something to the 3rd power. That means multiplicity of 3. All right, but if it has even multiplicity, this is the case of what we just saw here. It's going to come down and it's going to be tangent to the x-axis. Mrs. Hoffbauer calls that it kisses the x-axis. Some people refer to it as touches the x-axis. I call it a bounce. So if it has even multiplicity, if this factor shows up twice or 4 times or 6 times, it's going to come down, touch the x-axis, and then bounce right back off. So this is that case where I told you some books argue over whether or not this is an x-intercept. I would argue a bounce is not an x-intercept, but it is a multiplicity of a 0. Some books say, just call it an x-intercept. So I'll be a little open to interpretation on that question if that ever comes up, okay? Let's talk about these. These are in your notes. And they want me to do a whole lot of things, okay? First of all, they want me to apply the leading term test, and then talk to me about like what the ends would look like, and then determine the zeros, figure out who's repeated, which is already factored, so that's cool. Find some additional points. We're going to kind of skip that part for time. But on your homework, you totally would on your calculator. And then we're going to graph the function. You should be able to give me a decent looking picture without actually touching the calculator. And I say you should be able to give me a decent looking picture, not me. Okay, let's see what this looks like. First of all, you notice this guy's in factored form. So it's like the little factoring fairy came through and factored everything for you. So that's nice. By the way, I'm going to be skipping 6C, so if you need to use space, just scribble out 6C. Since it's in factored form, this second thing about determining the zeros, that's going to be real easy because it's already factored. Actually, the first thing is kind of hard for us to figure out. So figuring out the leading term is going to be tricky because it's in factored form. This is a factor, so I'm just going to write that down, negative 2x. All I'm interested in are the lead terms of each of the factors. This guy right here, this is x minus 4. All I want you to write down is the lead term of that factor, x. But be careful here, guys. Who is the leading term to this factor? If you took 3x minus 1 to the third power, think about that. You'd have a 3x, blah, 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 times a 3x, blah, 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 times a 3x, blah, blah, blah. What is going to be that very first term in this polynomial? This guy to the third power, this leading term is going to be a 27x to the third power. I know there's a whole bunch of mess that trails after it, but I'm only interested in the leading term right now. Guys, what is your leading term in this gigantic polynomial if we push this all together? Negative 54 x to the what power? 5th power. So your lead term, without foiling all this out, and I have kids every year who foil the whole thing out, which I think is a really big waste of your time. Don't do that. The leading term is negative 54x to the 5th. So don't draw me end behavior, just sketch the ends for me. What do the ends do? The left side goes up, the right side will go down. I'm going to come back to that thought in a minute. Okay, for part B, determine the zeros and state any multiplicity. Well, the zeros are going to be really easy for you to find because you just set each factor equal to 0. So like if you set negative 2x equal to 0, y'all will get x equals 0. There's one. If you set x minus 4 equal to 0, y'all get x equals 4. Cool. What happens, though, when you set that last factor equal to 0? I forgot what it was. Is it 3x minus 1? Okay, thank you. To the third power. So you'd be like, add 1, divide by 3, you get x equals 1/3. But how many times does this factor show up? 3 separate times. So like you'll get the answer, you'll get the answer, you'll get the answer again. So what you do on your math is you say you get 1/3 as an answer, but it has multiplicity of 3. Meaning it shows up 3 times algebraically. Alright, here's what I would do now. I'm going to put little stars on my x-axis on all 3 of these things because something happens at x equals 0, x equals 4, and x equals 1/3. I'm going to pretend this is 1/3. And I'm going to pretend this is 4. In order to get a good graph, I would have to get a couple more points. I'm not going to like bust out the calculator right now for this. Because the other clue we have is end behavior. So this end goes up. And then after this intercept, this end goes down. And what happens in between, I don't really know. But I do know that the multiplicity of 3 means that eventually it will cross through the axes, okay? So this graph is going to be like this. Yeah, you know what? That's actually not too bad. It's not. It actually doesn't look anything like that. That maximum goes up really quite high, I think. But pretend.
Okay.
So on your homework, you guys would just bust out your $150 calculator and be like, okay, that's what it looks like. But you should be able to find all of these things without me giving you too much insight from the calculator. All right. Y'all are going to do some bookwork for me. We posted the bookwork PDF plus the answer key, and you're working on factoring. Good luck.